Hello everyone, welcome to physics class. Today we are going to discuss equipotential surface. We have pictorially represented electric field using electric field lines. Electric field lines helped us to visualize electric field as well as it gave information about the direction and magnitude of the electric field. In a similar fashion, we can pictorially represent electric potential with the help of equipotential surfaces. First, let us see what is equipotential surface, and then we will see how it can be used to pictorially represent the concept of electric potential. Equipotential surface is a surface at every point of which the potential due to charge distribution is the same. Or we can say that an equipotential surface is that surface all points lying on which are at the same potential. Or also we can define equipotential surface as the locus of all such points which are at the same potential. Therefore, the potential difference between any 2 points in an equipotential surface is zero. So if we move a charge on an equipotential surface, no work is done. This also means that there is no force acting along the equipotential surface. This is possible only if the electric field intensity is perpendicular to the equipotential surface at all points. Now let us see some equipotential surfaces. So for an isolated charge, we can draw the equipotential surface like this. This is the electric field lines, and you know that the potential depends upon the distance from the charge for an isolated charge. So all those points which are lying at the same distance from the point charge will constitute an equipotential surface. So let me take locus of all points which are lying at the same distance from this charge. So obviously I will get equipotential surface in the shape of concentric spheric spheres. From the diagram you can see that the electric field lines are always intersect an equipotential perpendicularly, and you can see that no two equipotential surfaces can intersect each other, because if they do so, then at the point of intersection there are two values of equipotential which is not possible. We have already seen that no work is to be done to move a charge along a equipotential surface, but work has to be done to move a charge from one equipotential surface to another. Now let's draw equipotential surface in case of uniform electric field region. So uniform electric field regions are represented by parallel electric field lines which are equidistant from each other. So if you draw surfaces perpendicular to this, we will get in the form of sheets which are at potentials V1, V2 and V3. Similarly, you can draw equipotential surface in case of electric dipole, two equal positive charge, two equal negative charge, etc. One thing is to note here is that wherever the equipotential surfaces are crowded together, then it represents a strong electric field. Here you can see that the equipotential surfaces are crowded near the charge. That means the electric field intensity is very high near it. And as we move away, the density or the crowdness of the equipotential surfaces decrease. It indicates that the electric field strength also decreases. Now let us discuss some of the properties of equipotential surfaces. First one, we have already discussed, no work is done in moving a test charge from one point to another on an equipotential surface. We already know the work done or the potential difference is given by work done divided by charge. In case of equipotential surface, all points have same potential. That means the potentials VB and VA are equal, or simply means that delta V is equal to 0. This is possible only when the work done WAB is equal to 0. So we can conclude that no work is done in moving a test charge from one point to another on an equipotential surface. Second property, the electric field is always perpendicular to the element dl of the equipotential surface. First, let us see mathematically prove this one. So since no work is done on equipotential surface, we have the equation for work done, that is WAB is equal to integral minus integral A to B FE dot dl. FE is QE. Here we will take unit test charge. Then it is nothing but integral A to B E dot dl, which is equal to 0. This is possible only when E and dl are perpendicular to each other. So you will get E dl cos theta is equal to 0, or since E is not equal to 0, dl not equal to 0, only possibility is that cos theta is equal to 0 or theta is equal to 90 degree. Here I have a question for you. Find out what if the electric field were not normal to the equipotential surface. So here we have two quantities, electric field and potential. Now let's find out the relationship between electric field and potential. We know in order to move a charge from point A to B in an electric field, the external agent has to do some work. This work is against the electrostatic force of repulsion. And we know that the work done is given by minus F dot dr, or in place of F we can substitute the formula QE or Q naught E. So we will get WAB is equal to minus Q naught E dot dr. This is equation 1. Now from the definition of potential difference, we know the potential difference is work done per charge. So we have VB minus VA, that is the potential difference between the points B and A, represented by dV, is equal to WAB by Q naught. By cross multiplying, you can write the equation for WAB as Q naught dV. Now just compare the equations 1 and 2. Here you can see that both have LHS WAB. So RHS must be equal. So by applying this, you can write minus Q naught E dot dr is equal to Q naught dV. So both sides Q naught is common, so you can cancel both of them and then rearrange the terms. You will get E is equal to minus dV by dr. What is the meaning of this equation? dV by dr represents the change in potential with respect to R, change in R, or it is also called as potential gradient. And here we have a minus sign. So we can write electric field as the negative of potential gradient at any point. So we can also say that the direction of the electric field is in the direction in which the potential decrease is the steepest. Why decrease? Because negative sign is there. So wherever it is the steepest, that will be the direction of electric field. So you can write electric field is in the direction in which the potential decrease is steepest. So we can define the magnitude of electric potential is given by the change in the magnitude of potential. Sorry, here it is not magnitude of electric potential, it is the magnitude of electric field intensity. So magnitude of electric field intensity you can write intensity here. Okay, so the magnitude of electric field intensity is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at the point.
The next property says that equipotential surface indicates region of strong or weak electric fields. So electric field is defined as a negative potential gradient, just we have discussed in the previous point. So you can write E is equal to minus dV by dr, or dr is equal to minus dV by E. You know that between two equipotential surface, the difference in potential V2 minus V1 or VA minus VB, whatever it is, it remains constant, because for an equipotential surface V1 is constant, for the another equipotential surface V2 is also constant. Therefore the difference between them remains constant. So you can see that dV remains constant for two equipotential surface. dr is the distance between these two equipotential surfaces. So you can see the distance between the equipotential surface is inversely proportional to the electric field. So since dV is constant on equipotential surface, we can write dr is proportional to 1 by E. What it represents? dr is the distance between two equipotential surfaces and E is the electric field intensity. So if the electric field intensity is more, dr is less. Or we can say that equipotential surfaces are crowded together in a region of strong electric field. So you can write if E is strong or large, dr will be small. That is, the separation of electric potential surfaces will be small. That is, equipotential surfaces are crowded and vice versa. Next point says that two equipotential surfaces cannot intersect. We already seen that in case of electric field lines, two electric field lines can never intersect because at the point of intersection, they will have two directions. Similarly, two equipotential surfaces cannot intersect. Why it is so? Because if they intersect at the point of intersection, there will be two values for electric potential, which is not possible. Okay, so here you can see that we have seen electric field as the negative gradient of electric potential. Electric field is a vector. Let's see this equation. Electric field is a vector, potential is a scalar quantity, but the potential gradient, that is dV by dr, that potential gradient must be a vector quantity. Then only both sides will have vectors. So in vector form we can write E vector is equal to minus dV by dr into r cap. R cap is the unit vector. So even though potential is a scalar quantity, the gradient of potential is a vector quantity. So electric potential is a scalar quantity, whereas potential gradient is a vector quantity. So the negative sign, what it indicates, it shows that the rate of change of potential with the distance, that is E is equal to minus dV by dr. dV by dr is rate of change of potential with the distance. So the rate of change of potential with the distance is always against the electric field intensity. Okay, it is in the direction of decreasing electric field intensity, you can say.